Hi students, this video is the last one I need to make and it is about complementary machines. Now we have been talking about complementary machines for a good while now, saying that it's easier to make a machine for a positive characteristic such as does do a certain thing. So that's how if you get a descriptor that has a not in it, like does not contain BB, or does not have a multiple of 3 A's, something like that. It's easier to draw the machine for strings that do have the property and then flip the states. But there are some caveats to this algorithm that I want to point out to you on these 2 pages. First, let's just look at what we mean by complementary machines. Let me make sure my cursor is big enough for me to see it. My system here at home leaves a bit to be desired, but it's still not terrible. Alright, so over here, these 2 machines, these are parody machines. I hope you recognize them by now. This machine on the left accepts strings where the number of A's is odd and the number of B's is even. That's this accept state here. So what if you want strings where the number of A's is not odd or the number of B's is not even? Now I say or because, let me just do a little doodle here. If we've got, let me represent, I need a couple of different letters. Okay, so the little, no, I don't want to overload that. How about property X means that you have odd A's, property X. And property Y means that you have even B's. That's this machine. Odd A's, or this machine is represented by X and Y. Remember that logical symbol and? X and Y produces this machine, with this being our accept state. So what if we want not X and Y? What we want is the complement of X and Y. Remember, De Morgan's law says that you have to distribute the not, so you get not X, not Y, and you flip that operator over due to De Morgan's law. So the complement of this machine should accept strings that do not have odd A's or do not have even B's. That's what this machine does. If you're in this state, then you do not have odd A's. So that's good. If you're in this state, then you do not have even B's. And if you're in this state, you don't have even B's either. Is there something else that I'm missing? This one does not have odd A's but does have even B's. This one does not have odd A's and also does not have even B's. Yeah, that's the one I was not seeing. And then this one does not have even B's. Alright, so this machine is the complement machine for that. It's very easily obtained by just flipping your state types. So all these become accept states and that one becomes a non-accept state. Now look at these 2 machines down here. Are these 2 machines complementary? They look like they are, because this state over here is an accept state and this state over here is not an accept state. But they are not complementary machines because we omitted drawing in a trap state. If you send the string BB or just plain old B through these machines, what happens? Well, this machine doesn't accept B as a string or BB. Neither does this one. If 2 machines are complementary, every string that one of them rejects, the other ought to accept. And every string that the one accepts, the other ought to reject. That's what true complementary machines act like. The problem here is that we neglected to draw in the trap state before we did our flip thing. This would have been the machine if we had drawn in the explicit trap to here. And when we make the complement machine, that trap becomes an accept state. And you can't leave out an accept state. You can leave out the trap and the machine will still be correct, but you can't leave out this accept state. This now is the true complement of that machine. Even if you had omitted drawing in, even if you had taken this out, you omitted drawing in the trap state and left it implied, still to make a complement machine you have to do what is now done over here on the right here. That is the complement machine to the one on the left. So we really need to make sure before we do this complement algorithm that the machine, if it has a trap, has an explicit trap, because that trap state is going to become an accept state. Now look at these machines right here. Are they complementary? Well, they look like they are, because this machine has this state non-accept and that state accept. And over here we flipped them. However, if you run the string BA through these machines, look what happens. This machine can accept BA. BA. This machine can accept BA too. BA. Uh-oh. If they were truly complementary machines, any string that one accepted, the other would have to reject. The problem here is that these machines are non-deterministic. And in a non-deterministic machine, it is often the case that for some particular string, non-deterministic, for some particular string, there's more than one pathway through the machine. The string BA has that property here. You can do B and then come over here on A, or you can do B and then stay here on A, because there's two pathways out of this state. I'll call this state 0 and this 1. There are two pathways from 0 on A. One keeps you at 0. The other takes you to 1. You must make the machine be deterministic before you run the complement algorithm by flipping state types. So before you run the algorithm, then you need to do two things. Number one, I lost my cursor. Where's my cursor? Number one, add any missing trap. And number two, be sure the machine is deterministic. Make the machine deterministic. And then the algorithm is simply flip the state types. That's it. Now, here's the last thought. It says we have no simple algorithm for finding complementary regular expressions. But we could still do it algorithmically. Describe a way to find a complementary regular expression using algorithms that we've already learned. The only complement algorithm we have works on machines, and so what we have to do is, number one, use Rex to NFA. Now remember, you don't have to know this algorithm, but you do need to know that it exists. Use Rex to NFA to turn the regular expression into a machine. Then complement. Well, Rex to NFA usually produces a non-deterministic machine. So I don't want to erase that. It takes too long. So before you do that, you need to use NFA to DFA because you can't complement a non-deterministic machine. Use NFA to DFA. It'd be better to shrink it down, but we'll skip the minimize part. Use NFA to DFA and then complement. Oh wait, I said a minute ago you didn't have to learn this algorithm. You do. You do need to know Rex to NFA. It's the other one that I'm getting ready to put on here that you don't have to know. So you want to complement the DFA using the algorithm we just learned. And then as a fourth step, use NFA. Remember, all DFAs actually are NFAs that just don't use non-determinism, but they're still part of this category. Use NFA to Rex to get the regular expression out of the machine, or find an equivalent regular expression. This is the one you don't have to know how to do, but you should know that there is an algorithm that will do that. You just don't have to know the algorithm. All right, that's all for complementary machines, and that is all for the videos that you need to watch while I'm gone. Thank you so much. I'll be seeing you soon, I'm sure. Well, I'm not that sure. I mean, things can happen. Hopefully, I'll see you soon.